In this video, I'm going to talk about binding energy and then fission and fusion reactions. And we are going to talk about nucleus, and we know nucleus contains nucleons or protons and neutrons. And we have learned how to calculate binding energy of different elements in the periodic table. Say, for example, we calculated binding energy of uranium-235. It was about 1782.9 mega-electron volt. And we can calculate binding energy of, for example, oxygen-16, which is about 127 mega-electron volt. Binding energy actually is the amount of energy is required to break apart all bonds between nucleons, between neutrons, protons, neutrons. If we compare these two values, say, we see that uranium requires more energy than oxygen. Whether we can claim that oxygen is more unstable than uranium, the answer is no, because the 127 mega-electron volt is used to break all bonds between 16 nucleons, while this amount of energy here is used to break apart all bonds for 235 nucleons. Therefore, we are not able to compare these two values and conclude that oxygen is more stable. In order to be able to compare between these two nuclei, we need to calculate and estimate binding energy required to break apart one single bond inside the nucleus. To do that, we divide this binding energy by atomic mass, and then we calculate, for example, for uranium, it becomes about 7.6 mega-electron volt, and the value for oxygen is around 8 mega-electron volt. And now we can compare these two values, and it seems, it suggests that uranium-235 is more unstable than oxygen-16. Now, if we calculate all values of this ratio, we can produce this diagram. In the vertical axis, we see binding energy per nucleon, or Be divided by A. And in x-axis, we see mass number. In this graph, clearly we have two regimes, and we see here binding energy varies with mass number. In the first regime, this increase keep continue until a certain level, and we get here the maximum amount of binding energy per nucleon, which is for iron nucleus. But for the second regime, we have the change of binding energy as a function of mass number. But here we see the atoms become more heavier because the mass number is increasing. At the same time, they are becoming more unstable. You see here there is a slight decrease in instability of these nuclei. In order to find out and understand better what happened for the nuclei in this range, I draw your attention to and remind you about the atomic forces. We have seen that a strong nuclear force is a short-range force. It means that it can be applied just for a very, very short distances, say about 2 to 3 femtometer. 1 femtometer is equal 10 to the power of minus 15 meter. However, electrostatic force or Coulombic force act in all ranges, like this. Because we are talking about nucleus, it contains protons and neutrons, and protons are positively charged. And we know electrostatic force is the repulsion force here. and two positively charged repel each other, while a strong force causes these two positively charged particles attract each other. If we combine these two curves, we get the new curve as shown here in this figure. A horizontal axis is distance. We see that if we are in this range of distances, the strong nuclear force is the dominant force, and two protons attract strongly each other, while the electrostatic force shown by a blue arrow here is very negligible. A strong nuclear force in this range is 200 times bigger than the electrostatic force. But what happened in this point? In this point, there is a balance between strong nuclear force and electrostatic repulsion. We have attraction and repulsion which balance each other. Therefore, there is no force here. As long as we take distance and get two particles get more distance from each other, we get in this range where the electrostatic or Coulombic repulsion is the dominant forcing condition. And this is what happened for the elements or nuclei reside in this range. All these nuclei participate in fission reaction. Assume that we consider these two protons here. Their distance is far away and it resides in these ranges, which we have a transition between two different forces, short range force and also Coulombic force. And here you see that this particle is shaky. For example, if we just excite or bombard this guy by one other particle, say one neutron, what happened? This guy become just splitted into two lighter element but more stable, because as soon as we are moving this direction, elements or nuclei become more stable. This process is called fission, in which a heavy nucleus is excited by a neutron and the byproduct will be two lighter and more stable nuclei. Okay, if we bombard or shoot one neutron to this target nucleus, the byproduct will be two fission products which are lighter and more stable. Huge amount of energy is released, but three neutrons also are the other byproducts of this reaction. Now assume that we have a rod like this and we fill this rod with a number of target nucleus, and then we just shoot one neutrons, and this neutron interact with one of these nuclei. What happened? In this figure you see the story here. This neutron slam the uranium-235. Two lighter and more stable nuclei are formed. One of them is called krypton, and other barium. And three byproducts are neutrons here. These neutrons are now free to react with other nucleus, uranium nuclei, as you see here. And at each of these reactions, we get lots of energy release here. And if this change keep continue, we are not able to control the process and release of energy. Therefore, huge amount of energy is released. And this process, if we don't control, is actually an atomic bomb. However, if we could control, block these two neutrons and do some kind of control, the energy control of the system, and we are able to harness energy from this kind of fission chain, reaction chain, and that process is what is used in the nuclear power plants. Let's talk about fusion. The question is whether we can apply the same story as fission to fusion. It means that we pick up one atom and in this direction we just split this into two other more stable and lighter nuclei. But it's impossible because oxygen is more stable than other elements below. Therefore, this condition is not in place. In fusion, actually, two positively charged nucleons get close to each other. As an example, if we select hydrogen 2, which is called deuterium, and hydrogen 3, which is called tritium, and under very high pressure and very high temperature, we fuse them together. Then what we get is huge amount of energy released, helium-4 and neutrons. Hydrogen 2, as you see here, has 1 proton, 1 neutron. Hydrogen 3 has 2 neutrons and 1 protons. If in the chemical reaction form, it can be written as this reaction, helium plus huge amount of energy. This is a process that happens in the sun, and we can divide in 4 kind of steps. Here, 2 protons get under this high pressure and high temperature, get close to each other, so that the strong force in this range could just take care of these two similar charges. And then with this reaction, we get the release of energy and also the generate hydrogen 2 or deuterium. Then we generate tritium and then helium-3 as shown here. And the last step, using the helium-3 and the tritium, we generate helium-4. And in this process, huge amount of energy is released. And you see all kind of the elements shown in this table can participate in this kind of fusion reaction. And until getting here to iron, which is the most stable element. And this also shows how the sun layers and the structure is. For example, you see here we have different types of fusion, and we get all the way down towards the core, which is iron. And we see the hydrogen is the fuel of the energy generation on the sun. And if it's run out of hydrogen, then the sun starts to die out.